Learning. Thank you everyone for joining us on the third day of International Faculty Development Program conducted by Artificial Intelligence and Data Science Department of Ishwar Engineering College. We have two data science tools lined up today, Apache Spark and Keras. Without further ado, I would like to introduce our today's speaker, Firjan Joyce, Data Science Associate Engineer at Accenture Chennai. With 10 plus years of experience in software development, his work experience is splendidly massive. It encompasses machine learning, deep learning, Spark, data analysis, design and development, having in depth knowledge of full cycle development for building a data warehouse. Furthermore, he is the winner of hackathon conducted across North America markets in Accenture. We are content to have you today, sir. The session is all yours.
Great. Hey, thanks, Indusha, for um, the intro. Okay, so good morning, everyone. So I heard that you had a great two sessions, and hopefully this would be also a useful session for you. Okay, so before we get started, any questions you guys have, or shall I just go into the session right away?
And participants, you can unmute and any questions you can ask.
Okay, so I'll get started with Spark. Let me share my screen.
Participants are kindly requested to keep their mic on mute.
దొంగ మొగందానా ఏంది ఇది?
Sir, your screen is visible.
Sure. Okay. So today we'll look into Spark. Why Spark is such an craze in the market right now, and what are the interesting things that you need to know about Spark? And probably at the end of the session, we can actually take a look at some of the ways that Spark can be used, probably a live demo as well. So that would be the agenda for today. Okay. So before we go into the how Spark works and all those things, so let's talk about why there is a need for a Spark. And there are so many distributed computing technology available in the market, and why is the need for a Spark to start with? And before what we had Spark, we had a couple of other technologies. Hadoop was a famous one that was introduced by Google, which is used for batch processing, and it was a very powerful distributed computing platform. So with the huge volume of data, big MNCs like Google, Facebook, and all those companies produce every day, they needed a distributed computing platform. Otherwise, they could not scale up to their needs. So that was when they introduced Hadoop as a platform, and they needed a streaming processing as well. And at that point in time, they had a technology called Storm, and they needed a machine learning platform as well, right? So there are so many things that they needed to um, keep their business running, and that is where these technologies come together, and it was helping them. So when we talk about stream processing, and that it is also a very important, in terms of how they wanted to process the data, and every day, day in and day out, they churn out millions and millions of data, and they want to keep processing. And a quick example would be, right, you would be browsing through Facebook or Instagram and all those. So you like a certain product in Instagram, and instantly you switch to Facebook, you see that the same product is shown, ad for the same product shows up in Facebook. You are wondering how so quickly they adopted, and they found out that we are interested in product, and they have started selling as that product. So those are some of the main businesses of big MNCs like Facebook and all those, right? So that's when stream processing comes into picture, and machine learning is, as we all know, that machine learning is probably becoming hot topic in every market. So that is, machine learning helps in businesses in so many ways that we cannot actually keep track of nowadays. So everywhere we go, we see machine learning coming up, and you would be surprised in how many different ways we use it every day, but we simply don't know that we are using it every day. Okay, so the need for Spark is basically, right, so why there is a need for Spark? So they needed a single platform which can do everything for them together, and it's something that is more powerful than the existing Hadoop platform. So that is when Spark came into picture. So this Spark can actually handle multiple things like batch, streaming, machine learning, interactive, and also graph. Graph is some GUI based data processing technique. So these all are encompassed in Spark. That is why Spark is so powerful in this context. Okay. So, and also the interesting thing about Spark is it's a open source engine, which can actually handle so many things, but it's still open source, and that's actually a very good thing. And the key thing that Spark is unique about Spark is it processes everything in memory, which is much faster than the other processing techniques where they read the data, process it, again land it in another storage space, then again process it. But Spark doesn't do that. It waits for all the user inputs, creates an action plan, and then takes the data in memory, processes it, and then gives only the output to the user. So it's very effective and quicker in that sense. So that is why Spark is very effective. And the interesting thing about Spark is there are APIs that Spark provides, which different technology can adapt. So say, for example, Python, Scala, Java, and R. So all these things you can code in all these languages into Spark. So you don't necessarily need to learn a specific language to do Spark. If you know Python, you can do Spark. If you know Java, you can do Spark. R or Scala, any language, programming language that you are aware of, you can use Spark. So that is actually very very effective, in terms of businesses. Even I have seen within Accenture, I worked in projects that use Python, PySpark for doing data analytics, and I've worked in projects that use Scala, Spark. So it's all dependent on user preferences. Since Python is also an open source tool, so there is a lot of flexibility for businesses and the clients to work through this. So that is a big advantage that Spark has. Okay. So this is the history of Scala Spark. So if you see the history, the first thing is it was introduced in 2009 by Berkeley University. So that's when it was introduced, and in 2010 it was made open source, and finally in 2013 it was donated to Apache. So Apache made it a really effective tool to be used for across businesses, and became a top level project there, and it's the most active project in Apache by 2015. So here is a quick comparison between Hadoop's MapReduce versus Spark. So the big question is, if we have Hadoop already, why would we need Spark, right? So this is a quick comparison on why we need. And for us, sorting a data of 100 terabytes, around 100 terabytes, the time taken is significantly lesser in Spark, which is, and also if you see at other things, right, other parameters that is used, right, even without really fast read write speeds into disks, right? It is able to achieve that. The reason it is able to achieve that is it doesn't do a lot of read writes. It performs a lot of things inside its memory. So there is no need to do a lot of read writes, and that is the reason, one of the reasons it is actually able to do it so fast. So you have a single stack of application which can take care of your batch processing, your streaming processing, and also your interactive processing. So that way you can achieve your goals with simplicity. So that is, if you're talking about Spark. Okay, so these are some of the other features of Spark. So we can, it can develop sophisticated algorithms. It is compatible with an open source ecosystem since it's already an open source application. So this is an quick look at how the difference between how Hadoop and Spark performs operation, right? So Hadoop basically takes the data from disk, performs operation, and then again lands into the disk. But Spark does it a little bit different. It reads from the disk, stores it in memory, and then it performs all the operations one by one. Like, it will not wait for one operation to complete and then load it into the disk and again start from the beginning. It will do everything within the RAM, and then finally it brings out that output. So when we do the demo, you'll probably see what the difference on how it's different from other programming languages where you type in a command and immediately you see the response. But Hadoop doesn't do that. It will wait for all the instructions, and finally only when you specifically ask it to perform the operation, it will actually initiate that operation. Okay, so for every operation, right? So if you see so many times that Hadoop is actually loading the data into the storage disk, but Spark doesn't do that. It actually basically keeps all this information in the RAM. We call something called resilient distributed data set. So that is what stores the data throughout the process, and finally at the final operation, then that's when it lands it into the disk. So these are some of the other features. So this is something that you'd probably need to know. So the first thing that you would need to know is how an RDD or RDD operates, right? So it works in three different phases. So the first thing, it would take the data and map it into an RD. So that is where you read the data from the disk and then store it in an RDD. So that is the first step. The second step is where you perform the transformations like filter and if there is another operation like group by or all those things, aggregation, and all those operations are done in the second phase. And finally the collect phase. So the collect phase is when we give the action command to the Spark, which then it starts from the beginning. Then it actually triggers that process of processing, and then it will produce a result. So it's always a three-step process that we need to remember that Hadoop does. Unless you give that action command, that is a collect command, it doesn't actually start performing. It will keep waiting for that action command to start performing. Okay. So let's look at the architecture of Spark. So why the architecture of Spark includes some a master node and a bunch of slave nodes. And why is the need for a master node, and why is there so many slave nodes? Right. So when we look at the architecture of Spark, so there are so many slave nodes which basically take instructions from the Spark. So the only only purpose of that slave node is take the instructions and deliver. Right. So in certain cases, there will be so much slave nodes that are involved in the process. You would need somebody to monitor and share the workload equally across all the slave nodes, or else there will be a few slave nodes were operating at full capacity and other slave nodes might not be operating at all. To make it efficient and also to make it operate at full capacity, a master node is required. The master node basically find out which nodes are actually having the capacity to take more workload, and it will distribute it across the slave node. So that is the purpose of a master node. So the work that we give primarily, we are the user. So the work that we give to the Spark primarily goes to the masters. So there will be more than one master in certain cases to avoid to make sure that we have some redundant backup in case one master goes down. The work still continues. There is no hindrance. But primarily the task that we give to the Spark goes to the masters, and masters decide which slave to engage for which work, and that is how Spark operates internally. And the big advantage of having this master slave architecture is you could literally add n number of slaves to your master, and the scalability wise, depending on your the amount of work that you have, you could actually scale it easily. So that is one of the main reasons this architecture is very powerful. Right. So like I said, so the RDD is one of the key components of Spark. So to start with, we have something called resilient distributed data set. That's what in short is called as RDD. And it's just a simple collection of objects, or in other words, we could say it's just a collection of data, right? So the beauty of RDD is that what it can do is it can actually keep the data in memory. It doesn't have to land the data in disk every time it has to transform the data. It can transfer data from one RDD into another RDD, and then it can keep doing that until the final result is achieved. So that is what the significance of RDD is. And it could be an RDD, could be any object. It could be a Python object or Java. It could be in any object. So in our example, we are going to look at Python with how we are going to create RDD with Python objects. So say, for example, a list is a Python object, but the list object can be converted into an RDD, and it can be used as a resilient distributed data set. So how the RDD is very efficient is, within an RDD, the data is split into multiple partitions. So partitioning is a very commonly used topic in any performance-oriented application, right? So if you want to make the processing faster, data processing faster, you need to have partitions. So it's a very common terminology used. So what it really means, what is a partition basically is, to give you a simple example, right? You have a employee data, a file or table containing employee data, and it could have information about different departments. It could have, say for example, we could take a college for example. There it could have 10 departments within a college, right? So what this RDD does is basically it will identify some of the data and keep it in different partitions. Say for example, employee information of one department goes into one partition and another department goes into another partition, and it keeps in different partitions. The advantage of doing it this way is whenever there is a request to do some computations, or say for example to find out who is a top scorer in a department, or who is a top scorer department wise, who is earning the highest salary paid to which employee within a department. So those kind of computation, when it comes to that, there is the operations can be performed in individual partitions separately. So the RDD partitions, partition 1, the data in partition 1 is assigned to one slave, partition 2 is assigned to another slave. So every individual slave is engaged to perform the operations, and finally the master node consolidates all the response and the results from individual slave nodes and then publishes the result, which is not possible in a regular operational model. It is only possible in a distributed environment. So in a regular model, either it is done sequentially, or all the data is sent together to a single node, and it will take some time to do all the processing. By putting it into partitions, the data can go to separate slave nodes, and then the result can be published altogether much faster. Like if it's 6 partitions, you will probably see the performance 6 times more. So this is an example of how the data is sent to different partitions. It's just a pictorial representation of how each partition goes into different nodes, and the data is processed that way. Okay. So this is about the transformations and actions that RDD can perform. Okay, so what is a transformation basically? So why is a transformation really significant? So transformation is where the actual data manipulation happens. So there are different data manipulation terminologies you're probably aware of. A filter is one of them. If you want to take only certain data for processing, you apply a filter. If you want to do some aggregation, then you apply the group by. So aggregation in other terms is like you want to calculate an average of average salary of every employee in a department, then you need to perform an aggregation operation. So those are aggregation operations. And if you want to perform some operations on only one department, then you apply a filter. Right? So those are the very basic data operations that we perform day in, day out. So it is possible that we can do that in RDD as well. So the only difference is the RDD does something called a lazy evaluation. It will do operations only after we actually start the action associated, or until that the RDD will keep waiting for that action command or trigger command to perform the operation. And the action is what that actually triggers the job, and this can be done with a couple of commands like collect, reduce, count, and take. So this is the final action command that actually triggers all the previous commands that we have been giving to that, and finally it will actually execute all those operations together. And another interesting fact about RDD, like we talked, so it doesn't it can cache the data in its memory, the entire data in its memory, and there is no need to land it in any disk. And also it can transfer data from one RDD to into a different RDD directly, and there is and it can store the data in the RDD for the future operations, that the upcoming operations that it is going to perform. And this is a quick flowchart of how the operations are performed. So you take the parent RDD. So the first RDD is probably the one that you read from the disk, and you perform some transformations and you save it in another RDD. So, and then once all those transformations, after transformations, you just keep saving it into different RDDs, and finally you trigger that action, and it will perform all those actions right from the beginning, where we read from the disk and finally publish the result. And these are some of the features of Spark. It is like 100 times faster than Hadoop, and that there are memory management. It recovers automatically. Like I said, it has fault tolerance. It has backup for everything. So there is a backup. There is a redundant master node if in case one master node fails, and if there is one of the slave node fails, the master node makes sure that the task assigned to it is actually reassigned to some other slave node, so there is no failure at any point. So those are some basic features of Spark. Before we go into demo, so I would like to ask if you guys have any questions, any doubts in whatever we have covered so far, so that we can actually start looking at the demo. So I take it that we are on the same page so far. I saw somebody messaging, why we should choose Spark rather than other. Yeah, like I said, so there are other tools which are in the market, but Spark is primarily based on Hadoop. Oh, we Hadoop is relatively slower due to some of the reasons, um, and Spark is much faster. So that is one of the main reasons we should, we go with Spark. And it internally uses Hadoop architecture inside, but it is much faster because of the RDD processing and also some of the, um, you know, it has the ability to scale to any technology, right? Like Python, Spark, and all those technologies. Um, I'm not able to actually see all the questions. Let me try to. Okay, so um, Spark is not just a processing unit. It is a framework, to be honest. Like it has a lot of other components as well. It internally takes care of a lot of things. Like it actually makes sure that the processing is performed across all the slave nodes. It actually takes care of any fault tolerance. Any failure happens in one of the nodes, it actually internally takes care of that. We don't actually give any specific instructions to take care of that. So it internally takes care of all those things. And we have APIs on top of that, multiple APIs, right, on top of so it's actually a framework, to be honest. So it's more than a processing unit. It has a lot of other things that internally it does to make our life easier. Can use as academic purpose. It depends. We can definitely do a mini project, and I don't see why not. But to be really honest, the need for Spark comes in when there is huge volume of data, right? And that's when a need for Spark comes in. And if there is a small volume of data, you could simply do it with a regular database, and there is no need to have such a a distributed processing. But yeah, definitely for a mini project, and we can definitely if you have a huge data set and if you want to try to do some data analytics on that, you can definitely do that. Yes, Spark can process huge amount of data like deep learning for sure. Yeah, it can actually do it much better than deep learning, to be honest, because deep learning is a machine learning platform. Sometimes deep learning it's not optimized for performance. Spark is optimized for performance. It is just machine learning is one of the part of Spark, but the Spark is much more than that. It can actually do simple data transformation, analytics, reporting, and all those things, right? So it's actually an all-rounded tool. Yeah, and can we connect to a database? We could, I think, but I've never never worked on a situation where you had to fetch data from a database. But yeah, definitely that I don't see why not. But when we say database, right, databases contain structured data, and the need for Spark really comes in when you have unstructured and there is huge volume of data. So databases are more like when you have a structured data and then you don't have huge volume of data, and there is when you have so much data to process, and that's when we need that additional processing capability of Spark. Okay, so difference between an RDD and data frame. So data frame is a Python object, right? Like a list, or it is one of the Python objects. I think it comes so RDD is different totally. So RDD actually turns some of the Python objects into a resilient distributed data set. So so irrespective of whether it's a Python object, it's a Scala object, anything that holds the data is converted in RDD so that the data can be held in memory and processed faster. So that is a difference. Yeah, so why Spark is faster is it's a distributed processing framework, right? So that is why Hadoop was faster, and that is the same reason Spark is also faster. So there are multiple reasons it's faster. First thing is the distributed processing. You don't have a single server that takes instructions one after another and performs. So there are so many parallel nodes which are waiting for instructions. So the data is sent to them in parallel, and their results are returned in parallel. There is no waiting time, like it's not a queue kind of thing. It's like that is a big difference. It's faster. That is first reason. And with us compared to Hadoop, Spark is much faster because even in between the transformations, it doesn't land it in any storage space. It keeps it in memory even on the fly. So that is another reason Spark is faster than Hadoop. So does Spark belong to data transformation tool? Actually, it is both. So it can do data transformations. So data transformation, the purpose that we do data transformation is for data analysis, right? To be honest. So it can do both. So you can do data transformation and also data analysis. So data analysis is only comes after you do data transformation. So you cannot do any data analysis on raw data, right? So it can do both. Okay, so can you give example of structured and unstructured data? That is actually a very interesting question, right? So when we say structured data, so anything that you can think of an Excel sheet, right? Excel sheet, you always have a header, saying, and then you put the information in between. So just think of an Excel sheet, filled with data as a structured data. So unstructured data would look totally different. Say, for example, the data comes from Twitter, right? People keep writing their opinions. There are a lot of things in Twitter every day, their opinions, comments, and all those things. And this information, you cannot put it in an Excel sheet. If you just imagine that, you cannot put it, but there is information, but it is not structured. It's just people just keep throwing in random opinions, right? So if you ask somebody an yes or no question and they respond only with yes or no answers, then you get a structured response. But if you just ask their opinion, they'll just give you any opinion, whatever they thought and whatever they learned in their experience. But you cannot just keep it in an Excel sheet in a structured format or in a database in a structured format. But still, there is a lot of information in it. You cannot ignore it. So that's what really we call it as an unstructured data. Okay, so what is window criteria? Not sure. Are you referring to the streaming uh, streaming in Spark? Yeah, so there is something called a window criteria and while streaming. So there are different ways we can set the window. So if there is a 5-second window or 10-second window, that is the time window. It will wait for the data for that window and then process it. So that is one. So there are different ways to set up the window criteria. The Spark, so Spark acts as master or slave or both. Okay, so Spark is a framework, and masters and slaves and all are something that are created within the tool, the framework. So I can show you how we create a master and how we link that master to a slave. Those things I can show you probably in the demo. You can access it in, I think you'll be able to get from the Apache website itself. But I use a virtualized platform, which is easier for trainings like this. So I'll show you how I do that. if possible, which type save things? Data science. Yeah, so data science, the data science that we do, that we use for learning is only, we do with structured data mostly, to be honest, right? So we have a data set from some website, we download the data set and then we use that for data science. But we don't run into a scenario, we rarely run into a scenario where there is unstructured data. Yeah, so that is one of the reasons we don't use it in, we don't see it regularly used, but to be honest, Spark is used in a lot of places where they use for data analysis. Spark can I compile. I'm not exactly sure if we can use Spark on online compilers, but I use a virtualized platform, which is, this is apart from my work environment, right? This is a virtualized platform called Vagrant. So which will create a Hadoop distributed file system and also provide you a interface to access that. So that is what I'll show you in today's demo. This is not a platform that we usually work. This is not a client environment. This is a virtual environment I just installed purely for training purpose.
Sir, good morning.
Yeah.
So you said Apache Spark, it works in distributed environment, sir. What exactly
Right.
the concept of distributed environment, sir? You said.
Yeah, it's so when we say distributed processing, right? So say for example, right? I mean, if you create a simple web server, right? There is one server sitting somewhere, and you try to access it, and the request goes into that server and you get the response. And if 10 people try to access the same information, it will process one information after another. Everything is put into queue. So that is a regular processing, right? So that is how most of our computers and all those things work. There is only one processor basically taking instructions one after another. So that is a regular processing. So when you say distributed processing, there are more than one processors that are waiting to serve you. So that is basically distributed processing. So if
you mean multiple Sparks?
Not multiple Sparks. So there is only one Spark, but it will visualize individual processing nodes within that.
Okay.
So what happens is
inside this Spark, you say multiple processing nodes. You say correct, na? That's what you say.
Yeah, exactly, right. So it will virtualize nodes inside, so that there are multiple processing units waiting for the thing, and within that, the Spark will actually decide which task should be assigned to which processing node. And that way, there is no, the concept of waiting for one instruction to be over before the next instruction to be taken, it's actually reduced, and that way the processing is much faster. So that's what usually is called a distributed processing environment.
It simply sends randomly, or any criteria to send the particular one to particular node? Any criteria behind it?
The criteria is primarily, right, I mean, it will decide which one is less loaded, which node has capacity to take more instructions. So that way it is more efficient.
So it looks like a distributed computing system concept, correct? No? It decides where to send, who is the best processing unit for particular application, correct? No? That's what.
Yeah, exactly. Yeah.
Yeah. Thank you. Thank you, sir.
So let's quickly go into the demo session. Probably if there are no other questions. So if you see my screen, so this is actually a Spark environment. So I've already logged in. I can probably go out and start again. That way you know how I came in here.
You can stop screen, then
Okay. So this is I'm trying, like I said, I virtualized the environment. We already have a distributed framework um, uh, already set up. So right now I'll just log in using some default password. Okay, so if you see here, right, so once you log in, you can probably see there is a master node and there is a slave node. So worker node is basically a slave node. In this case, we don't have a lot of slaves. You have only one slave node, and then there is the data node, right? So that is what.
excuse me, sir. You are sharing the screen. Any?
Yeah, I'm. Oh, are you not able to see, sir?
Yes. No, sir. Screen is not visible.
Okay. Let me try to stop and. Is it visible now?
Yes, sir.
Okay. So if you see here, right, so when I try to, so these are the nodes that are available within. So we have a master node and a worker node. Um, so those are the things that we have. And once we have, set up your master and worker, actually, I can actually give you the commands for that as well. How to set up your master and slave and all those things. So you need to start your distributed file system. And once your environment is up and running, so these are the commands. I mean, just for your information, I can show you the commands. So first you need to start the master, then you need to start the slave, and then assign which master it needs to report to. So since we have only one master, I am assigning this to this master. So internally they are related to each other, and the slave will take instructions from that master alone. So that is actually something that we need to do before you actually jump into the environment coding and all those. Okay, so so there was a question, I think, how to get this screen. I can show you one more time. Okay, so so there is a virtual box which actually allows you to create an Hadoop pseudo environment. Okay, so once you install this Oracle virtual box manager, it's called Vagrant. The entire suite is called Vagrant. It will install your Hadoop environment. It will give you a virtual manager and all those. So once you install it, you can actually create a new machine like this, and it will start your Hadoop environment. So your Hadoop environment is up and running now. Then what you need to do is go into this, log into the server from any putties interface that helps you to log into Unix servers. So I'll use that to log in, and this is a default username and password it provides. in a real client environment, right, to be honest, the developers won't have to do all these things. There will be infrastructure admins who will take care of all the setup for you. You will be provided the environment now with all you have to do is start coding basically. Okay, so once you go into this, that's when we can actually create the master and slave and all those things. So since I already created master and slave, so it's all there inbuilt. So now there are APIs like we discussed. There are APIs available to perform this operation, right? I mean to give instructions and do coding and all those things. So let's invoke one of those APIs, that is your PySpark, which gives you that Python environment to you can start coding with Python language and then perform operations. So it says Spark version 2.1.1 and the Python version is 2.7.6 and all those things are set up. So now this environment is ready for you to actually use Python programming language in Spark. Okay, to save some time, I'll probably, in some cases, I'll just copy this code and then explain rather than typing from the scratch, since we have very limited time. So the first thing is, right, like we discussed. So I'll create a simple list in Python. So this is a simple list. And let's say, for example, I want to do square of this, right? So what I would do is use a lambda function. This is something called list comprehension in this is a lambda function in Python. So what it's basically doing is take each element from that list L and then assign it to X, and then that X is actually multiplied twice, and this will keep happening for every element in the list. So that is what that's what it is. So if you see right now, you'll probably, if I just so you can see that it created a new list with the existing list, squared each element in the existing list and created a new list. So that basic Python programming language, I was able to achieve this. Okay, so I have a few other examples as well, similar to that. I mean, say for example, if you want to apply, so like we saw earlier, right, there are three main operations that is actually performed. One is mapping. Mapping is actually basically taking the data from your Python object and processing it, right? So that is mapping, and most cases you would take from a Python object and save it into a RDD, which will look in the next steps. And the second important thing is applying filters and all those things, right? So that is a transformation part. So here's another example of how you can do some transformations on this. So you created a list of squares, and now you want to only take the even squares, say for example. So you just try to do a modulus 2, and if the remainder is 0, then it's we know that it's an even number. So similar to the earlier one, we are going to do a lambda operation, take each element from this list called squares, assign it to X, and that for each element you perform this operation. And whenever this operation returns true, this filter function is basically qualified to be sent to the output. So if you see from this list, only 4 is an even square, so it is actually filtered only that out. So that is the filtering operation that is performed. And finally, we have reduce operation. So reduce operation is also very significant. This is used specifically in areas where you want to do aggregation operations. Say, for example, you want to do some aggregation. It is used. Let me run this command and I can explain you how it actually worked. So it's actually taking the list with 1, 2, that list L that has values 1, 2, and 3. And if I see the result, you can probably see the result as 6. So what it basically did is it actually took the first element 1 and 2, and then it and assigned it as x and y, and then it multiplied it. So 1 into 2 is 2, and that result of that first operation is again reused for the next operation. So the next time when you next operation would be the result of first operation into the third element, that is 3. So first operation is 1 into 2, and the result is 2, and that 2 is again multiplied into 3, and the result is 6. So if I have a list that is actually bigger, say for example, so you can see how it actually performed that operation on each and every element. So first it did 1 into 2, and then the result is 2, and then it did 2 into 3, then the result is 6, then it did 6 into 4, right? And then finally it did the result of that with 5, right? So that's how you reached 120. So this will come in handy when you do actually aggregation operations, which we can actually take a look as well. Okay. Okay. So those are the 3 operations, right? I mean, so far we haven't done any RDD operations so far. So let's try to do some RDD operations as well. So there are 2 ways to create an RDD. I mean, there are 2 or 3 ways actually, to be honest. So there are 3 ways to create an RDD. First thing is you take a list and then use the parallelize command, and then then that will create an RDD. So that is the first way. And if you want to specifically create the number of partitions, like 3 partitions or whatever partitions, then you need to specify the number of things, so that it will take that list and then split it into 3 partitions and save it inside the thing. So that is how you create a RDD. And the second way to create an RDD is directly from a file, right? So you can actually, there is a command called text file. So this, what it will do is, if you have a file, it will actually take that file and then read that file and then create it into convert it into an RDD, and then if you save it in any variable, it will be saved in that variable. So then the third method is actually to take one RDD, do some transformations, and again save it into another RDD. So that is the third method of creating an RDD. So those are the couple of things that they should know. So once you create an RDD, like I said, unless you give that collect command or option command, it will not actually perform the result. So in this case, since RDD1 is created, I will show you the contents of that. So what it will do is it will actually take that instructions from all the 3 instructions. Say for example, from here, the num, this line, and these 4 lines are actually performed only after I gave the third instructions. Until then, it was just sitting there. It looked like it accepted the instruction, but it was not doing anything literally. It was just waiting for me to give the collect command. After I gave the collect command, it started from the beginning, created the nums object, then it created the RDD1 RDD, and then finally it actually printed that values. Okay. So that is a lazy evaluation. That's how RDD works. Okay. No need to install Python before using Spark, because those are, like I said, it's kind of a suit. Is the one that I'm using is actually everything is inbuilt. All you have to do is just create a virtual environment and then start working on it. Okay, so I think we should probably take a look at one example. Right, this would be an interesting thing. So if you want to find out how many occurrences of a word happens in a file, in a file, right, this would come in handy in sentiment analysis and all other areas. So let's create an RDD first. Read that text from a file and then create an RDD first. The second thing is I'm gonna do a take individual words, split the words like with a space as a delimiter. I'm gonna split and save those in another RDD probably. And then you can probably see what is there in the words. Okay, so this is what is there in that file, and that is actually printed here. So now I am gonna do a aggregation operations to count how many words are there basically. I mean, how many words, each word and how many times it is repeated. Say, for example, this is actually repeated twice. So ideally, it should say is there 2 times and all those things. So this is very effective, useful in sentiment analysis. So here we have Hadoop 2 times, and if there are words that are repeated and all those, then you can find out if there people are positive about a product, positive reviews or negative reviews and all those things. So this is actually a very basic step in that. So first thing is I'm going to do a mapping called, create a pair RDD, something which will assign the word and corresponding number to it. So it's for now, every word will have a number, default number as 1. Then I will use reduce by key operation to do the, sum of that, right? So for every time the word is repeated, it will actually do a sum. This is very similar to the other example that we saw here, where the reduce operation that we saw earlier, where it was actually multiplying one element with another, right? So so it's very similar to that. So here what it does is basically do the same thing. So since every word has a default 1, so when that word is repeated, it will actually simply increment it. So that's why we call it an aggregation operation. So for all the instructions that I've given, it is just waiting for me to give the action command. So when I give that action command, you can probably see that it's actually starting from the beginning and performing the operations. So now you can see how many times each word is repeated. Hadoop is repeated 3 times, and this is repeated 2 times. So this is actually one of the ways we can perform the reduce operations. I think we are over a minute. I thought of showing you a streaming example as well, but I think we are over a minute. Any quick questions on whatever we have looked at so far? Please feel free to. Okay, let's presume that you were able to follow whatever I was giving you. It was. Is there any drawback of Spark? Every tool will have some drawbacks for sure, but I mean, say for example, right? I mean, it doesn't support a lot of languages. It supports very few select languages. I think there are some machine learning ability it doesn't have. But again, those are things the extreme for people who are like extreme users or like a very advanced users. They will feel that disadvantage, and for beginners or like for regular users, they will not feel that they're missing something in Spark. think that wraps up the session, I hope. So thanks everyone for patiently listening. Appreciate your time. And thanks for this opportunity. Yeah. Thank you. Thanks everyone.
We have Kira's session lined up, right, sir?
Yeah. So shall we just go ahead and kickstart that as well, or do you want to take a small break, Mishra? Or do you want to do that?
That is up to you, sir. What
Oh,
would you
okay.
prefer? Would you like a break or can we
I'm fine.
continue?
I'm fine. I mean, if we can continue, then I'll be totally fine with that.
Yes, sir. Then we can continue.
Yeah, sure.
10-minute break we need. Are participants too fine with continuing with Kira's session or do you all need a break?
We
So
can
can we have
continue.
a break? So can we continue the session at 12:10? Would that be fine?
Yeah, no problem. But we'll come back at 10, 12:10.
Okay. Participants are requested to be here at 12:10 sharp. Thank you.
Yeah, sure, Indusha.
Yes, sir.
So, hope everybody is back from the break. So we'll probably get started with the next session. So the next session is on Keras. So Keras is one of the um, deep learning APIs that is very popular in the market. Um, Hope everyone is able to see my screen.
Yes,
Yes,
sir.
sir.
Thank you. Okay. So, so deep learning. When we say deep learning, so it's a neural network based machine learning algorithm, which it's gaining popularity a lot in the near um, recent times, and you can see the how exponentially over the period of years it has become popular, right? And it could do so many things that the previous machine learning algorithms could not actually perform, and it became groundbreaking in many ways. So we'll take a look at what are the things that it was able to achieve, and why deep learning is becoming more famous, and why Keras is becoming more famous as well. Right. So those are the things that we'll cover in this topic, and you could probably see machine learning experts saying why this has become, so so special. So why deep learning has become so special. So you see Andrew Ng, he's the founder, he's a professor in Stanford and a leading expert in machine learning, and he's saying, I worked all my life in machine learning, and I've never seen one algorithm knock over benchmarks like deep learning. And there is a specific, and there is a reason deep learning is so special, and um, we'll probably see why it is doing so good. Okay, and so Google is one of the leading companies which actually adopts machine learning into every product they build, starting from their search engine to their operating mobile operating system to their mail service, to every product they have. There is some form of machine learning in, and like I always say, you you will be surprised in how many different ways we have been using machine learning in our life without knowing that we have been using it in our life. So here are some of the examples, right? And how, so you could see, in Google Maps using machine learning and deep learning, right? Live traffic, you probably, if you use Google Maps, how the live traffic updates, show up in your map. Google Photos uses Google Maps. It can recognize faces and put the photos that you are into separate folders, classify them for you, and it works seamlessly. If you have used it, you will know that how a machine could actually do it so perfect, just like humans do. And then in Gmail, you could probably see it does spam detection. It moves your spams automatically to your spam folders, and it can actually perform a lot of other things, right? When you reply to mails, it can actually predict, it can suggest you words and correct your grammar and all those things, right? So those are things and it uses if you use Google Assistant, how Google Assistant is so good in recognizing your voice and then responding to that as well. So it was so powerful, and the Android operating system is filled with a lot of things, and the camera, especially the camera app and all those things, it can detect your faces, it can automatically correct the blur and all those things, and it can do portrait mode. You can shoot in portrait mode where it actually blurs the background and keeps the subject in focus, and all those things artificially without the actual optics associated with it. So those are so many things. And then you got YouTube, and so many the YouTube, you'd be surprised how the recommendation system in YouTube is so powerful in keeping it #1 streaming platform. The translations, robotics, image understanding, natural language. So many areas that we have been using deep learning every day. And what is deep learning is basically, you will see that artificial intelligence is the bigger frame, and it started in the early 1950s, and then we came into a phase where in 1980s we had machine learning. To be honest, the deep learning uh, papers related to deep learning were published much earlier, even in before 2000 and in 19 before 1980s, if I'm not wrong. But at that point in time, we did not have machines that could actually perform the deep learning algorithms, that can actually process the deep learning algorithms and train the GPUs and all those things. So it was on paper and theory at that point in time, and only when we had a powerful computers in our hand, we started actually doing breakthroughs in deep learning. Probably around 2000 2010 probably. Okay. So there are some basic things, and you're probably aware of some of these things, right? What is a feature, and what are labels, and what is training and testing and all those things. So features are basically the information that actually gives you some kind of input for that model to make a decision, right? So if you translate that to your regular life, everyday need. So if you want to um, make a decision, there is always something that actually influences that decision, right? So those influencing parameters are called features, and the labels are your output basically. So based on a certain set of influencing parameters, you will from your past experience or history, you would have made a decision, and that decision is recorded as label basically. So labeled examples are usually used for supervised learning, and for unlabeled examples are usually used for unsupervised learning. So and then we have train and test. So we take the entire data set, split it into two, so that you can train with one set and then test with another set. And we have different models like classification, regression, and all those models. So these are the sub areas of artificial intelligence. So you can see machine learning, natural language processing, robotics, neural networks, perception, and knowledge. So all these comes under the same umbrella called artificial intelligence. So deep learning is also an artificial intelligence, but it comes under the same umbrella. Okay. So what is machine learning, to be honest, right? So what is machine learning? So the simple definition would be, it's a type of artificial intelligence that provides computers with the ability to learn without being explicitly programmed. So that is a key word actually. So um, so for any data analytics that we have been doing, in the past, it was all pre-programmed basically. So for a certain criteria, we write some logic, and based on that, it will provide some reports. But machine learning um, gave a new area scope, an area wherein you don't have to actually write a program for the machine. The machine itself can actually start understanding things and learn, which is actually a groundbreaking achievement, to be honest. And some of the things that machine learning algorithms can do will surprise even humans. Even humans could not do some of those things, and that is actually becoming a reality now. Okay, so the first thing that you do is you take the label data and use the machine learning algorithm and create a learned model. And then once the training is complete, the label data is actually no longer used, and you would get new data, or probably you take the test data and run it through the learned model and then make the prediction. So that is how we do it. So the first phase is called training, and the second phase is called prediction, right? So those are very basic terminologies probably should know before we go into. And like I said, we have supervised learning and unsupervised learning. Supervised learning is when you have labeled data, and when you have unlabeled data, you do go with unsupervised learning. So the basic types of machine learning is you have classification and regression, which comes under supervised because you already have a label for that, like you already have labeled data set. And the clustering and anomaly detection comes under unsupervised. So you based on the data, you just identify something is off or something can be grouped together. So so feature engineering is interesting part. So feature engineering is what uh, uh, you know before deep learning came into picture. Feature engineering used to be a primary factor in deciding, making sure, making a machine learning successful. So an influencing parameter that influences a decision is called a feature. Like so when what are those parameters that influence a decision is something humans have to think through and then provide it to the machine learning algorithm. So if there is a parameter that has no influence on that particular decision, and you include that into the feature, that machine learning algorithm will not perform as good. So it is very important that we choose only the features that actually influence the outcome of that decision, rather than um, giving all the features and hoping that something will work. So that is what we call feature engineering. But with the advent of deep learning, the feature engineering itself uh, became something that deep learning itself could do, rather than we had to put in all the hard work. So that is a big advantage of deep learning. So it can itself figure out which features have more correlation to the outcome. So it will pick those features and use those features for training purposes. Um, so so this here it can clearly this slide actually tells you how we used to do machine learning before, where we used to do the feature extraction and only the classification or whatever the actual learning is done by the model. But with the advent of deep learning, it could actually figure out what should be the feature, and also it can actually do the classification. Okay, so here are some of the examples of where your deep learning is done extremely well. So the first thing is your image classification. In image classification, deep learning is probably the best thing that is available in the market. So it can actually perform really, really well to identify an object, in an image. And similarly, we have object identification, object recognition, and all those things. You have machine translation. So um, one of the um, sub one of the algorithms in deep learning is called a long short-term memory. So it is called an LSTM, or so that actually can take a sequence of inputs and provide output. So in this case, it can actually take sentences or passages from a different language and convert it into a different language, literally. So that is actually a machine translation that we do. And obviously, we can do sentiment analysis to know that whether the people are liking a product or not. So rather than you have to go and read through all the comments yourself, the machine can actually go through the comments and tell you whether people liked it or not. So that is a sentiment analysis, which is very popular in Facebook and all those things. So whatever is shared or when goes viral on a certain post that goes viral, um, Facebook can easily keep track of it to see if people are liking it or disliking it and all those things. And then if there is something they need to know that's disturbing that is posted in their platform, they need to take action. So those are things that it actually helps that way. So big companies, so they cannot employ people to do to keep track of everything that is happening in their platform. They deploy um, machine learning algorithms to flag things for us. And also fraud detection is another thing. um, you probably use it regularly. So fraud detection, so you probably seen that when you are using your card for payment and you used it happened to me a couple of days ago, and I was paying for something from a different location, and suddenly I got a call from HDFC saying that your payment is flagged as normally, and are you sure you are making the payment? And only after I confirmed that, they actually allowed. So that the way it happened is some algorithm is keeping track of all the transactions, and something anomaly happened, and it actually triggered an alarm, and some person intervened, and they had to make sure that it is happening. So those are things. It actually helps businesses in many different ways. And in medical field, like you could detect tumor, whether it's a malignant tumor or benign or what. So depending on the it could basically take your X-ray or your CT scan, or it could take your other test results and then determine your what kind of diseases that you're going through and all those things. And there are some groundbreaking algorithms that could actually outperform human doctors in diagnosing diseases earlier. Actually, so those things are happening in real world, which would actually become the new norm in future. And we have finance, obviously, right? So you can keep track of how well a particular stock would do, what will happen, and this you'll be surprised to know how many companies are actually share market or trading companies are actually deploying machine learning in their day in and day out businesses, right? So before we go into KRS and deep learning, so we saw some basics about machine learning and deep learning. So before we go into KRS, we should probably look at what is KRS, and because KRS term is very synonymous with TensorFlow, we probably think both are same. But there is difference, and there is an interesting story on how KRS and machine learning are synonymous, are related to each other, and how they are travel together over a period of time. So the primary difference is the Keras is actually a front-end API, but the TensorFlow is a back-end API. So the first thing is, originally Keras was developed by a Google researcher called Francois Cholet. So at that point, when Keras was originally created, there was nothing called TensorFlow at that point in time. So Keras was built as a front-end API, as an API for other backend deep learning libraries, right? So we had the other deep learning libraries called Torch, Ciano, Cafe, and all those libraries. And these libraries were a little complicated for machine learning experts to work day in and day out. So you could not go and just tell these libraries, go train yourself, give the data set and ask it to train itself. You have to actually write in assembly or basic languages to loop through each data set and then perform these operations, or probably do it in some C++ or basic language. So to make that life easier, Keras was actually originally built as an API on top of this. So Keras could actually support any one of these backend libraries, but it was an API where you could just go in and tell, give the data set and just ask it to just go train yourself, and it will go, and then perform all the looping and all those things in the backend and actually do the training. So because of its simplicity and how it was efficient, people actually flocked to Keras to use this API. So that was when Keras was the API for the backend deep learning libraries available like Torch, Ciano, and Cafe. And then at some point, Google introduced something called the TensorFlow. So, so if you want to understand what is, what is a backend and front end, you could take a similar analogy for similar to let's say you're building a web application, right? So your front end would be your PHP programming, and in the back end there would be some database. Say, for example, you're using a MySQL database to store your data, and the PHP program is actually interacting with MySQL and performing this. So the difference comes when the PHP programming and that is actually in the front end doesn't care what database is at the back end. So it could be MySQL, it could be Postgres, or it could be Teradata, or it could be any database in the back end. That programming language will be your front end interface and for the developer. to work with. So similar to that, you could take the same analogy in terms of Keras as well. So Keras would be your front end or your probably the API to this backend libraries, and Keras was becoming so famous. People started adopting Keras very fast because it was becoming so easy for developers. And that is when Google actually started building TensorFlow as a backend library, and TensorFlow was also added as one of the backend libraries for Keras. So originally, TNO was the default backend for Keras until version 1.12. But when TensorFlow gained popularity and become a famous backend, so at some later point in time, then TensorFlow became the default backend for Keras, and even for some time, Keras was still supporting other backend libraries along with TensorFlow. But very recently, when Google announced TensorFlow version 2.0, Keras has become the official high-level API of TensorFlow. And at some point, they announced that Keras would no longer support other. There would not be any new updates to support other backend libraries, and Keras became part of TensorFlow as is. And that is why now you see whenever you use TensorFlow, you use these commands called tf.keras rather than using keras as it is as a API. So this is actually interesting backstory that you probably is something when we hear keras, we would think that it is actually TensorFlow, but to be honest, it did not start it that way. So Keras was actually an API that was supporting multiple backend libraries, including TensorFlow, and then at later some point, it became a default. TensorFlow became the default backend for Keras. So that's how Keras is used. So back to our topic. So okay, I probably won't be going deeper into TensorFlow, but since TensorFlow is a backend for Keras, so these are some of the things that you should probably know about TensorFlow, and there are a lot of interesting algorithms that are available in TensorFlow. But even without TensorFlow, that you should know that even without TensorFlow, you can actually build machine learning algorithms with Keras alone, with probably a different backend library apart from TensorFlow as well, right? So why we need deep learning is a big question that so how do you so why we need a deep learning is an interesting concept that you should be aware of. So when you do a basic classification like this, right? So you have a bunch of points, to the left of the straight line and to the right of the straight line. So you could actually mathematically derive at a boundary that actually can classify. So it's just a straight line, and you could just put a slope to the straight line and say this is the boundary, right? And it is mathematically possible to do this. So when you go into some complex classifications, that is when you probably start realizing that, okay, in this case it's a little bit more complex probably, but you can still draw a boundary around it, right? So this is okay. But when you start going into situations like this, and it's the mathematical uh, boundaries that you could create around this is like too complex for for a human to actually come up with, right? You cannot write an equation boundary. The shape of this boundary is probably you cannot do it. So that is when deep learning is actually comes into as a very efficient tool. So how is deep learning such a, powerful tool is another interesting topic, right? So why not other, why is it different from others? So you probably learned it's how it is very similar to your human brain and neurons and all those things. So it can actually uh, adapt to the external stimuli. Every time it learns, it can actually, new set of information comes, it adapts and learns, and that way it can just much more powerful than your regular one. So what is the difference between regular one and a deep learning is that the deep learning model has more hidden layers. I think the limit is that just like two or more I believe is considered as a deep learning model. So with more hidden layers, it is very difficult for human mind to actually comprehend what the algorithm is doing, but the outcomes are much more accurate, and the results coming out of it is much more accurate with deep learning. Right, and then we have the activation functions that actually tell us whether we should how to classify that results, and then we have the training algorithms that actually fits the best boundaries, right? So gradient descent is a very famous algorithm that actually can fit, find the minimum cost and adjust the weights accordingly. So how do we now? So this is an example where we how a training is done, right? So if you see here in that graph, you start at some random point, and then you keep moving towards the the lowest cost. So that is what gradient descent actually does. Um, so the minimum is where actually the loss is at least, right? So that when there is least the boundary is in such a way that the there is very less error, to be honest, right? So when your classification is more perfect, then you say there is less error in the model. And there is a concept of overfitting and all those things comes in where you tend to fit it too much, and then it will become like fit too much and all those things. So those are like probably advanced topics that you will probably have to keep in mind when you actually start building machine learning. You cannot overfit, and it will actually literally, it becomes like it by hearts the answers, and then it will give the outputs that are response. Okay, so those are the things, and gradient descent. This is a very good depiction of how in every iteration it actually finds the minimum cost, and finally it will give you a best fit. Okay, so okay, so these are like other topics probably with too much information for a quick session like today. So I will probably jump into a quick demo where you could see how we can use actually a deep learning model to learn a real life problem. Okay. And if you're, so another interesting area where we do is image processing, right? So earlier we never had an opportunity. Image processing with other algorithms were too complex, and we had once we have had the deep learning, the convolution neural networks, it becomes much more easier with the image learning. So convolution neural networks are nothing complex. So if you consider each pixel as a feature, there will be for an image, for a full HD image, you would probably have 1080 into 1080p across, and then the number of pixels would be so large, and then it's very hard to build a model. I mean, the model cannot actually perform as with so many features. So to make things simplified, the convolution layer is built like to you take like couple of pixels surrounding to each other, and then make that, so in this example, that whatever is highlighted in orange is actually, converged into a single, convoluted, convolved feature. And this way, the number of features, the information in the feature is retained, and also the number of features are reduced, because in image processing, every pixel is considered a feature. So in when you take images, the number of features would be too high, and then your number of hidden nodes and everything will be too high for, and your machine probably will not be able to, cope up with that. So to avoid that, we create the convolved feature, and then use other techniques like max pooling and all those. And then finally, you reduce the number of features, but you try to keep the information intact as much as possible within each feature, and then you perform the regular deep learning. So that is what CNN is. Okay, so that is about the basics. So let's jump into this epic demo and see how it works. So today we'll probably, the thing that we are going to do is we are going to take a diabetes data set. So the diabetes data set has features like the age of the person, so a couple of other features. So about his, blood level, his cholesterol level, and all those things as a feature. So, and finally, it will have an output label, which actually tells you whether he has um, diabetes or not. So with that data set, what we are going to try and achieve is that we are going to try and find out whether we are going to train a model that can actually, predict whether a person is prone to diabetes, or a person has diabetes, just with knowing these features. So the first step would be, for you to import, these libraries like sequential and dense, so that you can use it to, create the model. So first, let's do that. Once that is done, so right now, if you're wondering, so this is actually a Google Colab. So Google provides an service that can actually be used to run machine learning models. And if you, especially when you're running deep learning and convolution neural networks, you will need a GPU, which GPUs. If you don't have a computer which has a GPU inbuilt, it would be really time consuming and processor intensive tasks when it does training. So Google Colabs provides you that option to actually uh, use their platform for training machine learning algorithms, and you can actually enable GPUs also if needed. So especially if you're processing image and all, then you cannot do it without a GPU. So that is the advantage of using a Google Colab. So this will actually, you can run it directly in their server, and it will actually do training and all this training in their servers. And so that even if you have a machine that doesn't have that processing ability, you can still run machine learning algorithms with this. Right. So the second step is basically, I'm just going to upload that data set to their Google Colab server. Okay, so it is asking me to choose a file, so I'm just going to choose the file that I already downloaded in my downloads folder. Then it will upload it into their server. So once it is uploaded to the server, all you have to do is start coding like as if it's as like a regular deep learning algorithm. So first step would be just load that data set in, load that actually file into a so now that I've loaded it into probably a data frame, now we can take a look at how the data is actually organized. So what this function is doing is actually it's taking actually the first 8 or 9 columns from the data frame and storing it into another data frame, and the last one is actually the label, right? So it basically contains only the outcome. So it will say either the person has diabetes or he doesn't have diabetes. So it will be just true or false kind of. So that is the output feature. So it is actually saved into your a different. So X is your features, Y is your label, right? So and you can see the features here. So when I run this, you can probably see all the features. So these are the numbers. I think I had the features. Yeah, so these are your features. So you have 8 features. Publish. So you have the parameters like if it's a woman, it is like number of times so she's pregnant. Then you have the plasma glucose, so medical parameters like so the blood pressure, right? So diastolic blood pressure is, I think it's blood pressure, and then um, so the insulin levels and the body mass index. Body mass index is your height to weight ratio, right? And then the age and all those things. So the reason they have picked these parameters are directly strongly correlated to the fact that he is diabetic or not. So they have picked these parameters and the data set has these parameters. So these are the 8 parameters that you actually see here. Okay, so the first one is probably the number of times pregnant, and second is the blood pressure and all those things. So the one row is an information related to one person, and the second row is another person. So that is how the data set is organized. Okay, so now let's build the model. So the first thing is you create a model, use the sequential model, and then you set up how many inputs you want. Since you have 8 features, so you are setting your input shape to 8, and then you could add different levels of depending on how many hidden layers you want. You can just say that here they have added another layer with 8 nodes and all those. And finally, the activation final output node, since it's a classification, it has to be one node. So based on that information that is coming out of that one node, you would actually determine whether it is whether he is diabetic or not diabetic. So, and that activation function that is used here is sigmoid. Right? So, if the value falls below 0.5, it is not diabetic, and if the value falls above 0.5, then he's diabetic. So that is what basically it means, right? So that's how sigmoid activation function works. And now we are going to do a training here. So the training, we need to have the optimizer and all those things. So we saw that gradient descent is one of the very common optimizer. So here we have used Adam. Adam is similarly another one, and then your loss function is also a binary cross entropy used here. So these are you could go with the default ones, and once you become well versed with other things, and then you can start fiddling with these loss functions and all those things, so that you actually can do better. So binary, why we use binary cross entropy is because this is a classification scenario. So we have a binary classification scenario. So that's why we use this loss function. Right? So once we compile this, and then your model is ready to fit. Right? So that is when we go for go for the training. So like we saw earlier, like we discussed earlier, Keras is so efficient this way, right? There is no for loop or anything that is written here. All you have to just, since this model, so all you have to do is just tell them, hey, this is your training features, this is your output label. Just go train for 150 iterations, and every, you know, um, every 10 data sets, every 10 rows, just update your weights. So batch size is nothing but, even though the entire data set is going to be trained for 150 times over and over, within within a one iteration, every 10 records, your weights will be updated. So it will not update the weights for every record. Depending on batch size, it will actually update it. So every 10 records, it will update. So if you have 100 records in your data set, your weights will be updated 10 times in one epoch. And in the second epoch, again, another 10 times. So that's how your weight gets updated every time. And then that's what it basically means. So the advantage of using Keras is all you have to do is just tell it, like, go train yourself, and then it will just start training. Okay, so let's just run, create the model, and then ask it to train. So now it's actually starting to train. You can probably see that, it's running, keeps running like epoch 90, 99, 110, 120, 150. So it has iterated over the same data for 150 times, and it has reached at accuracy levels. And if you plot this, it would be interesting to see how over a period of time it's actually doing better or worse, actually. So I think in this case, uh, one epoch, 150 epochs is probably little too much, because at certain point you can see the accuracy started at 63% and it reached what, 74, 75 at some point, and then it actually started declining. So you should actually find a sweet spot, the number of iterations to train, or else after a certain point it could actually start to decline also, right? I mean, if you go through gradient descent, you would know what would happen if it actually misses that least cost function. So those are things that you can actually do it in trial and error. You could try 200 epochs and 150, 100, and then see if your accuracy is, or what point the accuracy is best. And if you, it could actually sometimes go worse, depending on your steps and all those things. Okay, so now that model is trained, we can actually evaluate it with, and see what is accuracy. So right now the accuracy is actually 75%. The model can actually predict with given that features, it can actually, with 75% accuracy, it can predict whether that person is actually diabetic or not, even without with just with the features, it can actually tell you whether he's diabetic or not. It doesn't have to actually do a diabetic test to know with other features like his body mass index and all those things. It can. So how this is useful is, like, based on these features, diabetes can be prevented even before it occurs. The people can be warned that you are nearing the level where you could get diabetes very easily. So either you reduce your body mass index, you know take care of your other parameters and your blood pressure and all those things, or else you might end up with diabetes. So this would be a very good way to actually find out, even before people get affected with diabetes. They could be actually, it could be actually be prevented, and prevention is always better than cure, right? So so that's pretty much it. So finally you can actually see how it's actually predicted. So in reality, he's actually diabetic. Sorry, in reality he's actually diabetic, but our model is also able to tell that he's diabetic and all those things. So in case even if um, he is not diabetic, I mean he hasn't taken a diabetes test, with this features alone, the model will actually tell them like people with similar features are get affected with diabetes, and there's a good chance you will get diabetes or you already have diabetes, and that is a powerful way to actually persuade people to take care of their health, right? Health. So that's the demo that I have planned, and probably if there is any questions, we could actually go through the questions.
Hello, sir. Good afternoon.
Hi, sir.
And you said for the diabetic detection, what is the input samples you have considered, sir? Input samples.
Hello?
So this data set,
This
it's
data set.
actually right. So
Hello?
the data set, I think it is. Hold on. Can check the file directly.
கேக்குதாடா? ஹலோ? ஹலோ? சொல்றா.
And so I think probably.
Have you considered glucose level, sir? Glucose level, or what exactly?
No, so it doesn't consider the glucose level. So I think it's like around 800 or something. So these are the parameters that we have. I think it has blood pressure,
Okay.
body mass index. I think it has, it has plasma glucose concentration as well.
Okay.
So these are the parameters that are included, and it includes age as well. Some of these things. So these are the parameters that are actually closely correlated to a diabetic, person, chances of person being a diabetic.
Is this the correct parameters to evaluate diabetics, or we should consider more parameters? As I said, glucose level, percentage in the blood.
There could be, but so feature engineering is actually it's a separate.
So you mean we can consider any number of parameters? That's what you say?
No,
correct?
Not any number of parameters. So if the parameters that we pick should be
relevant.
Relevant, yes. So if it is not relevant,
I think for the diabetics, diagloose is a very relevant parameter. Correct, no, sir? Glucose
probably.
level.
I think it's already included, if I'm not wrong. I mean, I think they have a plasma glucose concentration. So I am not exactly sure of this medically what that does, but I think they have considered.
And also you mentioned that 75% prediction accuracy. Correct, no?
Right.
I think in the biomedical application, if you want to deal with detection and the prediction of diseases like, as you mentioned in the demo, brain tumor and cancer, why not 100% accurate? Because nowadays the cancer is a big problem. So people are not able to predict in advance, correct? Only it comes to only in the 4th stage and the 5th stage. So that time doctors are helpless. And why can we think of in a very accurate prediction kind of things, 100%?
So the prediction, basically, the reason some of the predictions are off, I mean not 100%, is primarily because of the features. So we do not have a lot of features that are accurate. But if you take an X-ray gives less information than a CT scan, and there is other scans which can actually give more information than a CT scan. So those are the parameters that actually consider give. But there, I recently saw model that was presented, and that model was performing better than actual doctors, because it from that scan report, the doctors were not able to tell that person really has cancer, but the model was actually predicting that he has cancer. But after a couple of weeks, when they took another scan, they found that there is a slight cancer there. So it's actually able to predict better than humans when the information is actually there. The entire information is there for it to actually process.
Yeah, and what I feel that, even whatever technology in the medicine, there is no rapid detection system. It's only kind of what I should say, random procedure, maybe because of this. So what do you say, sir? Can we think of this kind of a system, for rapid detection system? If the patient goes to the doctor, and there should be a system in a such a way that they should detect this is a what problem, so that they should hit the problem properly. So why, what kind of modeling we should look for? What do you say?
Right. So yeah, that is actually very good point, right? I mean, I think we worked on a proposal, I think, for one of the hackathons we had, which basically does this. So in the India, we do not have that level of medical histories maintained that well, but for one of our clients, we had proposed, one of our US clients, we had proposed that with the medical history that they have, we could actually go through that, even if it is handwritten notes from the doctors that they are visiting, we could actually do some natural language processing to learn his history and then probably come up with, some kind of prediction to see what are the potential, problems that he could get in the future and all those things. And it's the challenge is actually the training data or the medical history and the test results and all those things are not properly maintained. And if we have that information, I think the challenge is 80% getting that right features and the information data. The rest 20% is about building the model and actually doing that classification.
And the last question, sir, actually you talked about nicely about the diabetic prediction. Can we think of a very non-invasive, because even in the country, highest population is suffering from the diabetics. Every house, I think we see one person, somewhere, family in the family. Can we think of a very non-invasive kind of a system at home, so that we are able to monitor, we are able to, measure the diabetics? Is it kind of thing, some kind of a system or instrument? No need to go to doctor, or no need to go to clinic, giving a blood sample, wait for the response morning, instead of that, can we think of a homely, some kind of measurement? Is it possible?
Yeah, I mean, probably, I think it's probably a question for a doctor, I think. Yeah, I mean,
no, without doctor, can
yeah.
I measure my sugar just at home? Maybe
Right.
without
So
any taking
what I'm
blood
trying
out.
to say
Even
is,
today, there is an invasive method. Correct, no, sir?
right.
Yeah.
And I mean, yeah, probably, if there could be, I mean, I'm not 100% sure, if there could be something already in the market, we do not know. But if there is a way, like, since we are working with, on data analytics, right? So we work on the data that is available. As long as the data is available and it is relevant, definitely we can actually come up with a solution.
Thank you, sir. Thank you.
Yeah.
I have a question in chat, sir. Can ML algorithms process image datasets directly as that of DL algorithms?
Okay, so when we say ML algorithms, yeah, definitely. I mean, there are ML algorithms that actually does image processing. That is dedicated for image processing. I mean, but they were not that perfect because of the obvious reasons, right? So image processing is actually a much complex area. You need to do feature engineering perfectly to be able to do that. But the advantage of doing deep learning is that humans don't have to do the feature engineering. The machine itself will do the feature engineering. So as long as you are there in you are there in that image, it can actually identify your features and tell that you are in the image and you are sitting on the far right corner of in the image. But when you go for a regular ML and you need to be very specific, and which part of the image you are sitting and all, I mean, it's actually not that perfect solution compared to a deep learning model.
Hope that answered your question, Dr. Barona. And we have another question, sir. Can we use TensorFlow instead of Keras?
Yeah, that is actually a very interesting question, right? So TensorFlow without Keras is not possible. The reason is TensorFlow is a backend, like I said. So Keras is your API. So the TensorFlow cannot be independent, right? So now that term TensorFlow has become synonymous with everything together. Like Keras is also included inside TensorFlow, and now when people say TensorFlow, it's actually inclusive of Keras, right? Because so TensorFlow, if it has to be without Keras, it has to have another API inbuilt. So yeah, to simply answer your question, yeah, it cannot. It can without Keras, but it has to have another API apart from Keras. I saw a question just pop.
Can I read it out, sir?
Yeah, please.
Can you please tell me about pre-trained weights in TensorFlow? Question by Anita.
Oh, okay. So that is actually an interesting question, right? So I think so. Pre-trained weights are when somebody, when there is huge volume of data and there is huge, big processing capabilities are needed to make that, train that, okay? And you won't be able to do it sitting at home with your computer. And that is when your pre-trained weights come into picture. So you there is a way you can actually save that model or the even the weights into a file, and all you have to do is build your model rather than training your model from scratch, and then you can just load that into your thing. So that is what pre-trained weight means, I believe. So I mean, I think that's this question about, I believe. So that is actually useful when scenarios like that happen, especially in places where, say, for example, you don't have that, you are you are restricted to have that data. Like it could be a sensitive medical data or like something that you are not allowed to access, but you are allowed to have the trained weights for your purpose. So that is when it will become very useful. Okay, so for LSTM, I think that's what it means. Can we use Keras? Yes, definitely we can use Keras in TensorFlow. We built a tool actually with TensorFlow, sorry, LSTM, and we won a hackathon actually, with that tool. Um, that was conducted across North American markets. So the LSTM tool, what it basically does is it actually learns the sequences and basically predicts what comes next. So it could be similar to, you could think of your, when you go into a Google search and then you start typing something, right? So if I start typing like SRM, then it actually basically tells you what next, right? So I could ask who is the president of, so it basically understands what I'm trying to say, right? It's actually trying to suggest me what could be. So this is actually possible. This is basically actually done with LSTM. So it actually learning all the searches that has happened in the Google in the past, and basically it is actually predicting or suggesting that there is your next word. So the same concept we used in a code generation tool. So you probably are familiar with queries and SQL queries, right? So with the SQL queries, we are able to train for a certain client all the SQL queries that they have in the production environment, and based on that, when we start writing a query, like you start with select star something, and then you give some certain column names and all those, like you could claim amount, or if it's an insurance client, it could be like claim amount and member name and all those things. Then it will basically understand the context of what we are trying to get, and then it will start suggesting what columns you can get along with it, what tables you can find this column, and it will just start suggesting you based on its knowledge, because it has learned more than you, and it will probably give you more suggestions and all those things. So it is basically a code generation tool based on LSTM. We could actually do it in deep learning. I believe that is all the questions that we have.
We have another question right now.
Okay, so can you tell me about automizing ground truth in object detection? I'm not exactly sure, like what the ground truth is, but object detection definitely, and you can automate it for sure. There is it's nothing. It's not really complicated. So all you have to do is take a video file, like it could be a live video file from a CCTV camera, and then it could split it into individual frames. Um, and then each frame can be sent to an image on an object detection algorithm. So if it finds a face, or it could find a human, or it could find something in that, it will basically identify that and trigger an alarm, or probably notify the concerned people. Yeah, that is actually doable. Yeah.
As we are 16 past our scheduled time, can we complete the session, sir?
Yeah, sure. Thanks everyone for being patient and listening to this session. I appreciate and I thank everyone for giving me this opportunity, and I thank the HOD and the coordinators for this organizing this wonderful session. Yeah, thanks everyone. Have a nice day.
Thank you so much, sir, for such an in-detail and demonstrative session. On behalf of Department of Artificial Intelligence and Data Science and the entire fraternity here together, and on my own behalf, we extend a very hearty thank you to you, sir, for making today possible with so much insight and knowledge in spite of your busy schedule. Finally, the wonderful participants who have turned up in such great numbers, thank you so much for your cooperation. And tomorrow, 7 to 8 p.m., we have session on Vecca tool by Mr. Bhupati, Technical Associate Monza Research Lab, Cochin. And please make sure to fill today's feedback form circulated and have a splendid Sunday.
Pajin sir, thank you very much, sir, for accepting our invitation. And you have delivered very good 2 sessions continuously, and all the participants, I think, very satisfied in this session. Thank you, sir.
Yeah, thank you. Thanks, sir. Thanks for giving me this wonderful opportunity. Thank you.
Thank you, sir.
Thank you, sir.